Hello, Aman. How is the preparation for majors going on?
Hey Priyanka, I'm not understanding the PID controllers. Can you please explain me that?
Oh, yes, of course. First, let me explain how controllers are used. The way of writing an open loop control system is some input acts on a plant to produce output. Open loop system commanding is good where accuracy is not that much important. So, this is not good enough where we need accuracy. That is where feedback control comes into picture. What we do in feedback control is to feed the output of the signal to the plant so the system can adjust accordingly. An error signal is generated by summing reference signal and feedback signal. The controller converts the error signal to a command. PID controller term stands for proportional, integral and derivative controller. Let me explain PID controllers with the example of a car, where we use gas pedal to control the velocity of a car. The angle of pedal is theta. In this example, gas pedal position is our input and velocity of the car is the output. Also, we have a transfer function relating the input and the output, which is a low pass filter. By changing the angle theta, we can control the velocity of the car. Let's say the car is moving at constant velocity. Now, if we change the angle, the speed will increase a little bit faster. If we change theta at high frequency, the velocity won't get enough time to change. Hence, only low frequency input is allowed to pass. But while driving, we don't put theta at specific values. What we take care is the rate of change of angle. That is why we introduce an integrator to get theta from theta dot. Now, let us discuss use of proportional control. For example, when light turns green, you need to increase your speed from 0 to 25 miles per second. So initially there is a large error. Here, unknowingly, we are performing a proportional control. That is, we press the pedal faster. So as velocity increases to 25 miles per hour, the error gradually gets smaller and smaller, which gives zero steady state error. Consider the case when the gain is too high. Instead of pressing the gas pedal slightly, you apply large force. So the gain in velocity would be large. Its velocity will reach 50 miles per hour. At this point, the error will be minus 25 miles per hour. And then when you put brakes, the car will stop and the control system becomes unstable. Now let us discuss proportional derivative example. When we have to stop at red light, we need to control our reference position. Therefore, my new output is position, for which I introduced an integral controller. When we started at green light, the error is large, but it tends to 0 as we arrive at the next red light. So the error in position will go to 0. But as we are still pressing the pedal, we get past the light. Then we have to use back gear, which makes the error negative. Same problem again occurs and we will end up oscillating back and forth. To avoid this problem, we use PD controller. That is, while adjusting the position of pedal, now you are taking care of the rate of change of error. That is, you start releasing the pedal a bit early. In a way, proportional part is trying to get you to desired position, while derivative part is trying to restrain you. Now let's look at PID controller. If you are, let's say, at some distance behind your friend, but you both are going at same speed, there is an error associated. By increasing the gain, the distance between both the cars is shortened. By controlling the pedal's position using PD controller, the steady state error cannot be brought to 0. So, use an integral controller. The integral term sums up the error and increases the pedal's position, and so the car can be held constant at exact position we need. Now, we can get a 0 steady state error too. So, this is how we use PID controller in control systems.
Thank you Priyanka. This example has cleared my concepts regarding PID controller.